Hey everyone, my name is Annika, and this is chapter 13 of physics, where I'll be covering light and reflection. So this chapter is divided into three main segments that I'll be covering on video. The fourth is color and polarization. However, that's not covered at physics at Menlo Atherton High School, so I will not be looking at it in this chapter. So the sections I will be covering are characteristics of light, flat mirrors, and curved mirrors. This segment focuses on section 13.1, which is characteristics of light. So in previous chapters, we've been covering waves. We looked at that in terms of general waves and wave equations, and also in terms of sound. When we're looking at light, we'll continue to use waves, but these are electromagnetic waves, which are essentially related to all of the waves that we've been studying. When we're looking at visible light, this can be separated into the 6 colors of the visual spectrum, as I've drawn. They're red, orange, yellow, green, blue, and violet. And those colors make up visible light, or the light that we can see. Now, it's important to keep in mind that not all light is visible. In fact, only a very small portion of the light that exists can be seen with the human eye. Some light that isn't visible, for example, includes X-rays, microwaves, and radio waves. Non-visible light waves are called electromagnetic waves, which are waves that consist of oscillating electric and magnetic fields that radiate outward from the source at the speed of light. So we're going to look at light as this wave with electric and magnetic fields, as I've drawn in green and purple, and these fields are at right angles to one another. So when the wave is moving, that's how the fields work. There are these two waves, and then they add up to form the black arrow, which is the direction in which the light is moving. We can divide electromagnetic waves into what's called the electromagnetic spectrum. This essentially has all the different kinds of waves, and then their frequency, and some examples of how they might be applied. So as you can see over on the left side, we have the different types. These include radio waves, microwaves, infrared waves, visible light, which is those 6 colors that we can see, as I drew on a previous slide. Then there's ultraviolet light, X-rays, and gamma rays. And I've also written out frequency ranges for each of these in the second column. And then finally, we have some examples. So as you can see, for example, microwaves are used in microwave ovens. Visible light is used in photography. Ultraviolet light is used for sterilization, usually of medical equipment. And then I've listed the rest. I won't read them all because you can see this chart. And we'll be referring back to it in the future for reference for the wavelength when we're using light in equations. So when we looked at sound waves in previous chapters, we were using the speed of sound through air as a reference. Light also has a known speed through air, which is about 3 times 10 to the 8th meters per second. That's the speed of light, and obviously that's the speed at which light waves are going to move. So we can apply our same equation from before for velocity of a wave, where v is equal to wavelength times frequency. So that's how fast a wave is moving. However, in this case, we'll express this v, or velocity, as c, which refers to the speed of light, or 3 times 10 to the 8th meters per second. If we're looking to approximate the movement of light waves, we can use Huygens' principle. This uses wave fronts, which are lines of particles in a wave, as I've drawn in black, and establishes certain point sources along the wave fronts, which I am scribbling in blue right here. From each of these point sources, you can draw a ray towards the second wave front, which forms the radius of a spherical, or part of a spherical wave, which is called a wavelet. Those are drawn in red. Then, by drawing the line tangent to the wavelets in black, you can approximate where the second wavefront will be located. The rays can also be used to derive the properties of this wave, because they're just treated as straight lines that are perpendicular to the wavefront. So that's one way of approximating the motion of a light wave. We can also measure the power or strength of a light using intensity, which depends on the distance from a light source. So if we have, say, a light bulb, this light will have both a power input, which is in watts usually because of power, and a light output, which is sort of how much light it puts out into the environment around it. The rate at which the light is emitted from the bulb is known as luminous flux, which is measured in lumens, or Lm. That just basically measures how much light is pouring out of a light source. Once we've looked at intensity, we can also use illuminance to look at how a light is working and how brightly it's shining. Illuminance is defined as luminous flux divided by surface area, or lumens per meter squared. Those would be the units. And a way to think of luminous flux is, say we have this light source, which I'll draw here in red. It's emitting light. This light would form spheres. I'll just draw parts of the spheres. But you would get the idea that the light spheres would become larger and larger as you move farther from the source. Now, if I draw some lines to approximate sort of along this surface, how the light is coming out of the light source, you can see that the area becomes larger and larger as you move out to the bigger spheres. This means that the denominator of the illuminance would become larger, making the entire value smaller. So illuminance decreases as you move away from the light source, and thus the light becomes less bright to the eye. So now that I've gone over some of the characteristics of light, let's do some practice problems. Number 1. What is the frequency of an electromagnetic wave if it has a wavelength of 1 kilometer? So in this case, we'll be using the equation I just went over, where we have c, or the speed of light, is equal to lambda, which is wavelength, times frequency. And that, again, parallels our basic velocity equation for waves. So in this case, c, which is the speed of light, will be 3 times 10 to the 8th. That's how fast it moves. Then we have 1 kilometer, so that would be 1,000 meters in wavelength. We have to keep these units consistent. And then finally we have the frequency. So by dividing both sides by 1,000, I can solve for frequency, which I get is about 3 times 10 to the 5th hertz. Number 2, what is the approximate frequency range for orange light? So I'm going to start off with some known values that you can look up in your textbook if you need to for future equations. The values I'm going to plug in are the wavelength range for orange light. And it's just known that this is a range of 6 times 10 to the negative 7th meters up to 6.25 times 10 to the negative 7th meters. So now that we know these wavelengths, I'll call this lambda, we're ready to solve for the frequency range. So let's start with the lower end, the 6 times 10 to the negative 7th meters. We'll be using our same equation where c is equal to lambda times f. I'll plug in the speed of light for c. Lambda, wavelength, we know is 6 times 10 to the negative 7th meters, and then we have f, which is what we're solving for. By dividing both sides by 6 times 10 to the negative 7th, I get that the frequency is equal to about 5 times 10 to the 14th hertz. Now let's solve for the upper end of wavelength. Once again, there's this equation where c is equal to lambda times f. c is 3 times 10 to the 8th meters per second. Lambda is 6.25 times 10 to the negative 7th, and then we have f to solve. If I divide both sides by 6.25 times 10 to the negative 7th, I can isolate f, which is now approximately equal to 4.8 times 10 to the 14th hertz. So now that we have these two values, the lower end and the upper end of the frequency for orange light, we can see that it ranges from 4.8 times 10 to the 14th hertz all the way up to 5 times 10 to the 14th hertz. Number 3. Gamma ray busters are objects in the universe that emit pulses of gamma rays with high energies. The frequency of the most energetic bursts has been measured at around 3 times 10 to the 21st hertz. What is the wavelength of these gamma rays? Alright, so this is another situation where we'll be using c equals lambda times f, or again, the speed of light is equal to wavelength times frequency for a light wave. So 3 times 10 to the 8th will be the speed of light. That's equal to wavelength, which we don't know yet, times the frequency, which we've been told is 3 times 10 to the 21st. I'll divide both sides by 3 times 10 to the 21st to isolate lambda, which I find is equal to 1 times 10 to the negative 13th meters. That would be the wavelength for these gamma rays.